Hi there, this is Jose from Effex, and today I'm going to talk you about the catalog of OMARS design that can be accessed using the Effex platform. So let's start by remembering what a response surface design was. So these are experimental plans used in product and process optimization that involves the study of several quantitative factors and where the goal is usually to estimate a complete second-order response surface model that has main effects and second-order effects. This is two-factor interaction effects and quadratic effects. The most known designs are the central composite design and the box-Benken design. On the other hand, we have three-level screening designs that are also used in product and process optimization. They also involve quantitative factors, and the goal is the estimation of a partial second-order response surface model that has all the main effects and some second-order effects. The most famous design is the definitive screening design. So let's look at those designs for four factors. So we are going to see the most popular three-level designs for four factors that are the central composite design, the box-Benken design, and the definitive screening design. So we have chosen to show the color map and correlations of those designs, which are those graphs, and they quantify the correlation between the columns of the model matrix and the different effects. So for the central composite design and box-Benken, you can see that the main effects are orthogonal to each other, to all second-order effects, and the two-factor interactions are also orthogonal to each other and to all quadratic effects. For the definitive screening design, which is a smaller design, you can see that the main effects are orthogonal to each other and to all second-order effects. And this is actually what makes them OMARS designs. And it's exactly what I have said for the definitive screening design. So that the main effects are orthogonal to each other and to all second-order effects. And this is what defines an OMARS design. So they are orthogonal, main effects, they can be estimated independently from each other. They are minimally aliased because main effects can be estimated independently from all second-order effects. And they are response surface designs because they allow the estimation of a partial or complete second-order effects model. Now, a practical case, say that you want a four-factor experimental design. So here we have displayed the three options for four factors, factors on the horizontal axis, number of tests on the vertical axis, and the box-Benken central composite and definitive screening design. So you can see that definitive screening design is a very small experimental plan. If we make that graph for different number of factors, we get those lines. So DSD, definitive screening design, has very low number of runs. It is roughly twice the number of factors. Then you have the central composite design that grows exponentially. So the size is actually very large for a relative small number of factors. And the box-Benken design, the BBD, that's somewhere in the middle. What is the motivation of building a catalog of OMARS design is to know if there are designs in between. So if there are designs that they have the same properties and they have a number of tests that lies between the number of tests of the small definitive screening design and the large central composite design, which is this area. And the answer is yes, there are many, many, many designs. So this is a table with the enumeration results. This table is from 1 year ago, so the numbers they have already changed. But you can see that, for example, for 6 factors, from 14 to 40 tests, there are more than 100 million designs. How did we find them? So So we have a mining algorithm that enumerates non-isomorphic design. This is important because two designs are isomorphic if you can obtain one from the other by permuting the rows or permuting the columns or changing the signs of one or more columns or any combination of those operations. And those designs are actually equally good or equally bad on their statistical properties. So all OMARS that we obtained, they have the properties that we have stated. We use integer programming and high throughput computing, so these large facilities. In total, we are over, I think, 800 years of computation time. That of course it ran in parallel. This is an example, so this is a 5-factor 22 run OMARS design, which is a fold over design. It is balanced for main effects and it has no center runs. Of course, if we will add center points to any OMARS design, it will stay OMARS design because it doesn't change the orthogonality properties. And this is a second example, 23 run OMARS design, which is a non-fold over, has no center runs, it is balanced for main effects, and this is actually an optimization experimental design because it allows the estimation of a full second order effects model. Now, the last part of the talk is on how to choose an OMARS design for a specific problem. And I will be giving you two examples, one about an optimization experiment and the other about a screening experiment. So let's start with the optimization one. So imagine that you need an experimental plan for 4 quantitative factors and consider the standard designs, which are the central composite design with 26 runs and 2 center points, and the box banking design with 27 runs and 3 center points. In this table, you can see the most important quality attributes of those designs. So power to detect interaction effects, which is very high for the CCD, very low for the BBD, and the other way around for the power to detect quadratic effects. The maximum fourth order correlation, which is high for the CCD, low for the BBD, as we have seen previously with the slide with the 3 color maps. G efficiency much higher for the CCD. Prediction variance similar, and the pure error can be estimated because all 2 designs, they have multiple center points. Now we have chosen 14 OMARS designs and we have plotted a scatter plot with the maximum 4th order correlation on the vertical axis and the number of runs on the horizontal axis. So we have plotted the Pareto front, which are the red dots, and you can see that the BBD is on the Pareto front, but the CCD isn't. And we're going to focus on those 2 OMARS designs with 22 and 25 tests. So here we see a table with the quality attributes, and you can see how the power to detect interaction and quadratic effects is more balanced, because actually there is a trade-off. So the higher the power to detect interaction effects, the lower will be for quadratic effects if you compare designs with the same number of runs. And this is something that we can do because we have a catalog, so we can balance those 2 powers. Maximum 4th order correlation is on the low side, and I want to point out the pure error, so the last row. For the second OMARS design, you can see that it allows the estimation of the pure error because it has replicates, but differently than the CCD and the BPD, it has 2 different points in the design region that are replicated. So the estimation of the variance is pulled from the estimation of using those 2 different points, and the lack of fit test is more powerful. Let's change to screening. This is the color map of the 22 run OMARS design, and this is the color map on the 25 run OMARS design. Actually, you can see that the 24 rank OMARS design it has the same properties, orthogonality properties as the CCD and the BBD, which is what we call strong OMARS designs, where the two-factor interactions are orthogonal to each other and to the quadratic effects. So there are optimization experimental plans competing with CCDs and BBDs. Very few exist, but very often they are smaller than these reference designs, so they are very interesting. So this is the 4-factor 25 rank strong OMARS design that we have seen, and this is a bunch of 6-factor 40 rank strong OMARS, which are smaller than the CCDs and the BBDs for 6 factors. Now, yes, let's change to the screening example where we will show how you can choose an OMARS design for screening purposes. So say that you need an experimental plan for 6 quantitative factors with no more than 22 runs. The benchmark designs in this case are the definitive screening designs with 16 to 22 runs. I want to have a few words about one of the quality attributes that we use to quantify the quality of an experimental design, which is the projection estimation capacity. If this number equals 3 for a 6-factor design, that means that with using that design you can fit a full second-order effects model on any subset of 3 factors, and there are 20 subsets of 3 factors. That means that you can fit a large variety of different models. Now the benchmark designs are here, and I have highlighted 3 different rows in this table, so are DSDs from 16 to 22 runs. Now the power to detect interaction effects is very high. This is typical, that's good. The power to detect quadratic effects is very low, which is very typical for definitive screening designs, so this is not that good. And the maximum 4th order correlation for these small DSDs is also very high, which is not that good. So similarly, let's take 15 different 6-factor screening OMARS designs, and we will compare them to the benchmark. So here we have scatter plot with the power to detect quadratic effects on the vertical axis and the number of runs on the horizontal axis, and the Pareto front is again displayed in red color. The DSDs are not in the Pareto front, and we're going to focus on those 2 designs with 16 and 22 runs. So they are here, and we can see how again it happens what I said before. So the balance to detect interaction and quadratic effects in the power, it is better for OMARS designs, because at the cost of a small percentage of the power to detect interaction effects, you can gain also power to detect quadratic effects. Maximum 4th order correlation is below the DSDs, and I want to point out the 5th row, which is about the projection estimation capacity. That's for the OMARS design with 22 runs, it equals 3.8. What does this mean? So this means that using this design you can fit a second order effects model on any subset of 3 factors and 80% of the subsets of 3 factors. And you see that all the other designs, they have a value of 3, and that means that with these designs you can fit no second order effect model on any subset of 4 factors. So what are the weak points of standard designs? As we have seen, well, the central composite design, there is no flexibility in the number of runs, they are expensive, high correlation between quadratics, and low power to detect them. The Box-Penken design, no flexibility again, expensive designs, and low power to detect interactions. And last, the definitive screening design, they have a high correlation between second order effects, low power to detect quadratic effects, and limited projection estimation capacity. Advantages of using OMARS design catalog: you have flexibility in number of runs, In the catalog, we have all standard OMARS designs, so the central composite design, box banking design, definitive screening designs, they are also there, and if they will be the best for a specific challenge, then they will be chosen. Using our platform, you can consider multiple criteria while choosing a design. And for optimization, there are cheaper alternatives to CCDs and BBDs, and the weak points of CCDs and BBDs can be overcome. And there are strong OMARs, as we have seen. For screening, there are higher projection estimation capacity than the DSDs, so you can increase substantially the possibility of doing screening and optimization at once. You have higher power to detect curvature and lower correlation between the second order effects than the DSDs. In summary, the catalog offers much flexibility in choosing a design, often improves DSDs for screening and CCDs and BBDs for optimization. And our catalog also allows finding a design for novel problems, like for example, screening design in blocks with a higher power to detect quadratic effects. And the availability of a complete catalog allows us to develop a multi-criteria selection approach. So this ends my talk. I hope that you have enjoyed, you have learned something new about OMARS designs, which is a very interesting family of experimental plans that they can be accessed using the Effex software, and hope to see you soon.